what the velocity graph and position graph would look like for the car just rolling down the track. There are some rules, and I'll explain them, but this is the experiment, and we're going to take physical data to compare it to the experiment. Fair enough? All right. So with that in mind, the detector is the origin, right? It can only see positive distances in front of itself. It's limited. It can't see on both sides, so I can't get negative positions. I can only get positive positions. And truthfully, I also can't go to zero, right? So what I would like you to do is tell me, if I was to use this system to take data for the car sliding down the ramp, what would I expect to see for my velocity graph and my position graph? Now, I went over this yesterday. So for those of you who need some notes, who need direction, I'll give you direction. For those of you who can do this, go ahead. Don't wait for me. But I would put forward that for those of you who need direction, you need to ask yourself 4 questions for each of these graphs. Okay? I'm going to lay out the questions. I'm not going to write them down. If you want them, you write them down. So, velocity graph first. I think it's the easier one to do. And the reason is straightforward. Most of our current things that we are studying will have nothing more complicated than a constant acceleration. So our velocity graphs are likely to be flat or linear. Okay? Now, here are the 4 questions. Before you start, recognize this graph is about velocity, how fast the car is going. Question number 1, how fast is the car going at the start of the interval? Is it slow or fast? Question number 2, I'm just giving you the questions. Question number 2, in what direction is the car going at the start of the interval? Towards the detector, negative. Away from the detector, positive. Question number 3, how fast is the car going at the end of the interval? Question number 4, you see where I'm going with this. In what direction is the car going at the end of the interval? Towards the detector, negative. Away from the detector, positive. 4 questions. Ask those questions, draw some dots, connect the dots using the most reasonable way possible. Then we move on to the position graph. Position tells us where the object is. I know I'm going fast. Am I going too fast? These questions largely repeat themselves. So I'm hoping you use those little marks to indicate same thing, just different time. So for position, it's where. And for our thing, it can only be positive. So when we're dealing with this artificial laboratory example, we can only have positive positions. But that's artificial, right? Because that's the what we have stuck with us for this lab. That doesn't have to be true in nature, right? In nature, stuff can be anywhere. However, at time 0, is the object close to the origin or far away from the origin? That's where the dot goes. At the end of the time, is the object close to the origin or far away from the origin? That's where that dot goes. All right, same question, 2 points in time. Question number 3. At the start of the interval, is it going fast or slow? You already have the answer from the prior graph, right? But this is a decision tree because you have to make some decisions. Fast means shallow slope. I'm sorry, fast means steep slope. Slow means shallow slope. Because on a position graph, it's the slope that tells you velocity. So first, is it going fast or slow? Because that means steep or shallow. Is it going towards or away? Because that means negative or positive. At the end of the interval, is it going fast or slow? Is it going towards or away? Because that's steep or shallow. positive or negative. So you should be done drawing your pictures, right? Or you have enough information to draw those pictures? So, yes, sir?
How long is the track?
2.2 meters. I don't think that matters, though. I'm not going to use all of it. So, you guys ready to go? We want to compare reality with your expected outcome. So let's work this a little bit. Velocity first. At time equals 0, is the object going fast or slow? Slow. Maybe 0. I mean, if I'm lucky, and I haven't been yet today, I might be able to capture it going 0. At the end of the interval, is it going fast or slow? Definitely faster than it was. Positive or negative? Connect those in the best, most likely way possible. Do you guys believe that the car is going to increase its speed in a regular and reasonable way? Straight line. Doesn't have to be a straight line, but right now we're dealing with constants. Would you agree that the angle of this is constant? Seems reasonable. Position graph. Time equals 0. Is it close to the origin or far away? Close, but it can't be 0, can it? Not with this detector. So I'm going to start it somewhere not at 0. And then, at the end of the interval, is it close to the origin or far away from the origin? Far away. I need hints about the slope, so I'm going to take my hints from what we already talked about. At time 0, the object is traveling slowly, so I'm going to have a shallow slope. But it's traveling in a positive direction, so I'm going to expect it to be a positive but shallow slope. Maybe perfectly flat, if I can get it to be 0. After the end of the track, is the object traveling towards or away from the origin? Positive slope. Faster or slower? Faster. Steeper slope. There we go. Right? I want to connect them in the most reasonable way possible. My predicted outcome. That's what I expect. Let's see. All right, we don't have lots of time, and I want to be able to take our evidence, try and have some reinforcement here. So at time 0, is the velocity fast or slow? Fast. Towards the origin or away from the origin? That's what, negative or positive? After I put a dot down there at the bottom. After a couple of seconds have passed, is it going faster or slower? Slower. I'm going to assume it's still traveling towards the origin because we're only taking 2 seconds of data. So slower, towards the origin, still negative. Good? Connect those in the most likely way possible. What do you think? Straight line. All good? All right. Probe can only see what's in front of it. So our positions are all going to be positive. Did it start close to the detector or far from the detector? Far from the detector. At the end of the interval, close to the detector or far from the detector? Now I need to deal with the slopes at those 2 points. Clearly negative and steep, right? Clearly negative and not steep, right? A reasonable way of connecting them I missed the point, but it's okay, isn't it? We're all friends here. You'll forgive me? Because I only have a couple of minutes. So shall we take a look at the data? So again, we noted that this is a trapezoid, and we're finding the area of that trapezoid by highlighting the data. And you guys are hopefully going to get me what the area of the trapezoid is, because that will be our displacement. I'm waiting patiently. It's not hard. You're just going to be adding 0.2 to 0.96, then multiplying by 2, and then dividing by 2. Yes? 1 point what? All right, so this area, 1.16 meters? Does that make any sense at all to you? Although we just saw on the track that it matches up, that it's close, that it works. What does the area stand for again? Displacement. Change in position. What's the symbol used in math for change in? The delta symbol, which looks like a triangle. Position, one dimension, I'll just say X. A location on a number line is X. Bar over the top because it's a vector quantity. And what did we have on the horizontal axis? What was plotted there? Because that's the height. What was plotted? What was the value collected? Time. Lowercase t seems to make the most sense for that. That 0.2, what did it represent? How fast it's going, right? And that's how fast at the start of the interval. So that would be a velocity, because it also is positive. It gave us direction. And B2 represents the velocity when? The end of the interval, the end of our time, t. You can put an F there if you want final. Traditionally, I don't. I'm just taking the things off the graph and making a generic relationship, because any system in which the object has an initial velocity and final velocity and accelerates at a constant is going to produce the same kind of trapezoid. I don't want to graph everything. It would be nice if I have ways of just making calculations. However, we should finish this up. Since we calculated, 1.16, and it started, again, at 0.4 and ends here, which is right around 1.5, that's all right. I'm okay with that. That's pretty nice, especially knowing at the end we had that weird hiccup in the data. So I think this is pretty compelling evidence. This has a shape to it, right? Now, you may not be convinced that it's parabolic because you guys like to say, well, it's exponential. I think we can prove what it is. It might take a little more convincing to prove what it is. Yes, it is true. Calculus can tell us. But the problem with calculus is that most of you who have had calculus have a very difficult time explaining what the calculus is actually doing. This is pretty concrete evidence. Would you agree? I like the concrete nature of this, because what it should help you actually do is it should help you be convinced that the fundamental theorem of calculus works in a very real and direct way from evidence. Newton wasn't just doing this in a box, right? He was trying to create a form of mathematics that matched what he was getting from experiment. And he had a lot of people's shoulders to stand on when he did. So him and Leibowitz coming up with different versions of calculus that went to the same ends, not accidental. Nature does this, right? So calculus isn't just something theoretical. It's a reflection of how nature works. Now, that being said, for people who need to rewatch this, and there will be some of you that will need to rewatch this. So this is going to represent the track. And we're going to place the motion detector at one end of the track. So I'm just going to use a little box to indicate the motion detector. And I'm trying to, I guess I want to line it up like it is on the table. I want to line it up like it is on the table. Motion sensor there. And I'm going to put a car on the table. Then I'm gonna take the whole thing and put it in an angle. This is the car. It's a Dynamics car, has a plunger, stuff like that. We'll see this stuff in a couple of days. But does this kind of match what I have here in front of me? All right, so we're gonna place the car at the top of the ramp. We're gonna release the car. The car is gonna make its way down the ramp. And when I release it, 1/1000, 2/1000, I'm thinking I need to create a 2-second experiment because I wanna take measurements for about 2 seconds. That's about how long it takes the car to go down the ramp. Now, I want you to pay attention again, because what I actually want you to do is I want you to consider visual learners. You all like to say that, even though generally you're not. You're just visual lookers. That's what we're looking at? Although, something happened with these wheels. So again, I'm gonna start at the bottom. I'm gonna hit the collect button. And I'm trying to push it before I hit the collect button. You guys hurry. Ask yourself your 4 questions for each graph.